Hello, in this lecture we'll find out the radius of a circle using two different methods. In the drawing we have a triangle ABC that blocks this circle, or this circle is inscribed by triangle ABC. In addition, we know that angle ABC, this angle equals to 60 degrees, and this angle ACB equals to 75 degrees in its size, and side BC equals to 2 units in its length. Again, our mission is to find out the radius R of this circle. We'll start with the first method, and we'll do a construction, that is to say from point C, we will draw perpendicular on side AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. By doing this construction, we rendered the right triangle BDC. So I copy the right triangle BDC in a new page and we will analyze it. So actually, this is the right triangle BDC that I copied from the original drawing. Angle DBC equals to 60 degrees and BC equals to 2 units according to what is given as the question. On this right triangle BDC, cosine 60 degrees equals to dB over BC. So I write it down. Cosine 60 degrees equals to dB over BC. dB, so cosine 60 degrees equals to dB over BC. BC is 2. So we've already found out that cosine 60 degrees equals to dB over 2. Cosine 60 degrees is 1/2, so 1/2 equals to dB over 2. Here we multiply this equation by 2, and finally we get that dB equals to 1 unit in its length. dB equals to 1. Here, this line segment dB equals to 1 unit in its length. We continue to focus on this right triangle DBC. On the right triangle DBC, sinus 60 degrees equals to DC over BC. Sinus 60 degrees is equal to 3 over 2, and it is equals to DC over BC. BC is 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. We will multiply this equation by 2 and finally we get that DC equals to the square root of 3 units in its length. Line segment DC equals to the square root of 3 units in its length. We will continue to focus on the right triangle DBC. The sum of the angles in any triangle, and especially in the right triangle DBC, equals to 180 degrees. So which angles we have inside the right triangle DBC? We have this angle that is 90 degrees, plus this angle that is equal to 60 degrees. 90 degrees plus 60 degrees, it is 150 degrees. Therefore, the missing angle must be equal to 30 degrees in its size. So write it down. This angle equals to 30 degrees. And it is given us the question that the big angle ACB equals to 75 degrees. This is the big angle that is equals to 75 degrees in its size, minus the small angle that is equal to 30 degrees in its size. The big angle minus the small angle must be equal to this missing angle. Okay, 75 degrees minus 30 degrees, it is 45 degrees. So the missing angle equals to 45 degrees in its size. That is to say, angle ACD, that is the missing angle, equals to 45 degrees in its size. In the next step, I will copy the right triangle ADC in the new page and we will analyze this right triangle ADC. So actually, this is the right triangle ADC that I copied from the original drawing. This is the missing angle that we found, that's equal to 45 degrees in its size, and we have already found out that side DC equals to the square root of 3 units, its length. The sum of the angles in this right triangle ADC must be equal to 180 degrees. So which angles we have inside the right triangle ADC? We have this angle that is the right angle is equal to 90 degrees, plus this angle that is equal to 45 degrees. 90 degrees plus 45 degrees, it is equal to 135 degrees. Therefore, the missing angle here must be equal to 45 degrees in its size. So, those two angles are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. In front of those two equal angles, we have those two sides that are equal to each other. That must be equal to each other. So side AD must be equal to side DC. AD equals to DC. We have already found out that DC equals to the square root of 3 units. So we can write here that DC equals to the square root of 3 units. And from this equation, AD equals to DC equals to the square root of 3 units. We will derive that AD also equals to the square root of 3 units in its length. AD equals to the square root of 3 units in its length. This side AD equals to the square root of 3 units in its length. We can write down in the original drawing that side AD equals to the square root of 3 units in its length. We continue to focus on this right triangle, triangle ADC. On the right triangle ADC, according to the Pythagoras theorem, here by PT is a version for Pythagoras theorem. According to the Pythagoras theorem, AC squared equals to AD squared plus DC squared. So AC squared, that is the square of the hypotenuse, equals to AD squared. AD is square root of 3, therefore AD squared is square root of 3 squared, that is 3, plus DC squared. DC is also square root of 3, therefore DC squared is square root of 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. We take a root out of this equation and finally we get that AC equals to the square root of 6 units in its length. AC equals to the square root of 6 units in its length. Here, side AC of triangle ABC equals to the square root of 6 units in its length. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is inscribed by triangle ABC is equals to the radius R equals to the area of triangle ABC that blocks the circle over S, that is the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter of any triangle is equals to the perimeter over 2. So the domain of this rule, rule number 15, is here. We have a circle that is described by this triangle, triangle ABC. So the radius R of this circle, according to this rule, rule number 15, will be equal to the area of triangle ABC that blocks the circle over the same perimeter of the same triangle, triangle ABC. We can actually implement rule number 15 in our drawing. Why? Because in our drawing we have a circle that is described by a triangle, and whenever you have a circle that is described by a triangle, you can implement rule number 15. So according to rule number 15, the radius R of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. Repeat again. The radius of our circle, the radius R equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. According to rule number 15, of course. The area of any triangle is equal to the base of the triangle times the height to the base over 2. All divided by S, that is the semi-perimeter of triangle ABC. We take the base of this triangle, triangle ABC as AB, and therefore the height to the base will be CD. So the base is AB, and the height to the base must create 90 degrees with the base. So CD is the height to the base, while it creates 90 degrees with the base AB. So the height is CD divided by 2, all divided by the semi-perimeter of triangle ABC. So AB is equal to 3 plus 1 times CD. CD is equal to 3 divided by 2, all divided by S. So this expression is the area of triangle ABC, and we have to divide it by S, that is the semi-perimeter of the same triangle ABC. So the radius R of our circle, the radius that we are looking for, equals to the square root of 3 plus 1 times square root of 3 plus 2, that is the area of triangle ABC, divided by S. S is the semi-perimeter of the same triangle ABC. And the semi-perimeter S equals to the perimeter over 2. The perimeter of triangle ABC equals to AB plus AC plus BC. Is AB plus AC plus BC divided by 2. So the radius R, the radius that we are looking for, equals to the square root of 3 plus 1 times square root of 3 over 2 divided by AB is square root of 3 plus 1 times plus AC. Here AC equals to the square root of 6 units, so it is plus square root of 6 units plus BC. BC equals to 2 units according to what is given as the question, all divided by 2. So this expression is the area of triangle ABC, and the value of this expression is 2.366. That is to say, the area of triangle ABC equals to 2.366 square units divided by S, that is the semi-perimeter, and the semi-perimeter of triangle ABC equals to this expression, and the value of this expression in total it is equals to 3.591, and 2.366 over 3.591 equals to 0.6589 units. Repeat again, the radius R of the circle, the radius that you are looking for, equals to 0.6589 units. That is the answer to our question. Repeat again. The radius R of this circle equals to 0.6589 units. We finished with the first method. In the next step, I present to you how to find out the radius R of this circle according to the second method. The second method, we define the center of this circle here as O. We define the point of tendency of tangent AC with this circle as F. We define the point of tendency of tangent AB with this circle as E. And finally, we define the point of tendency of tangent BC with this circle as D. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle, that is equal to R according to our definition. We can implement here rule number 1. According to rule number 1, the tangent to the circle is perpendicular to the radius drawn to its point of tendency. We have here tangent AB, that is tangent to this circle point M, And we have the radius OM that is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. According to this one, rule number 1, we can actually implement all 1 in our drawing. Why? Because in our drawing we have the radius OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to rule number 1. Likewise, we join points O and D together by a straight line. OE is the radius of this circle that is equal to R. The radius OE is drawn to point E, and therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and F together by a straight line. OF is the radius of this circle that is equal to R. The radius OF is drawn to point F, and therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We can implement here also rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have a circle in the drawing, and the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule number 1 in our drawing. Why? Because in our drawing, if you focus on the common external point, point C, on the common external point, point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CF equals to CD. CF equals to CD according to rule number 2. Likewise, we focus on the common external point, point B. From the common external point, point B, we have two tangents to this circle, tangent BE and tangent BD. And according to rule number 1, they are equal to each other. That is to say, BE equals to BD. BE equals to BD according to the same rule number 2. In the next step, we join points O and C together by a straight line. And we join points O and B together by a straight line. And we prove that those two right triangles can go into each other. That is to say, we prove that the green right triangle BOE is congruent to the yellow right triangle BOD. So I write it down. We prove that the green right triangle EOB is congruent to the yellow right triangle OBE, OBD. So why those two right triangles congruent to each other? First of all, side OE of the green triangle is equal to side OD of the yellow triangle. They are both the area of the circle, therefore they are equal to each other. Repeat again. Side OE of the green triangle equals to side OD of the yellow triangle. They are both the area of the circle, therefore they are equal to each other. Equal to R. In addition, side BE of the green triangle equals to side BD of the yellow triangle according to rule number 2. Here, BE equals to BD according to rule number 2. Okay, again, BE equals to BD according to rule number 2. And finally, we have the common side, side OB. OB is the common side that belongs to both triangles. So can I know that OB equals to itself? It's the common side that belongs to both triangles. Repeat again. Side OB equals to itself is the common side that belongs to both triangles. So actually proved that all the three sides of the green right triangle EOB are correspondingly equal to all the three sides of the right yellow triangle OBD. Therefore, those two right triangles converge to each other according to side rule. That is to say, the green right triangle EOB is congruent. This is the sign of congruent to the right yellow triangle OBD according to side rule. And from the fact that those two right triangles congruent to each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding angles, those two corresponding angles must be also equal to each other. So this is angle EBO in the green triangle. And it must be equal to this angle that is actually angle OBD in the yellow triangle. Again, angle EBO equals to angle OBD. So if we define one of those two angles as theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees. That is to say 2 theta equals to 60 degrees. Here we divide this equation by 2. And finally we get that angle theta equals to 30 degrees in its side. So this is angle theta, that is equal to 30 degrees in its size. In the next step, I will copy the right yellow triangle OBD in a new page, and we analyze this right yellow triangle OBD. Actually, this is the right yellow triangle OBD that I copied from the original domain. This is angle theta, that is equal to 30 degrees in size, and side OD is the radius of the circle, that is equal to R. So in this right triangle OBD, tangents 30 degrees equals to OD over BD. OD is R, so it is R over BD. R over BD. In conclusion, found the tangents 30 degrees equals to R over BD. Here we multiply this equation by BD, and we get that BD times tangents 30 degrees equals to R. Here we divide this equation by tangents 30 degrees, and finally we get that BD equals to R over tangents 30 degrees. So here, this line segment BD equals to R over tangents 30 degrees in its length, so I write it down. BD equals to R over tangents 30 degrees. We repeat on the same process on those two right triangles. So we'll actually prove that the right orange triangle ODC is congruent to the right pink triangle OFC. So I'll do it quickly because we have already done it on those two right triangles. So the right orange triangle ODC is congruent to the right pink triangle OFC. So why the pink triangle is congruent to the orange triangle? First of all, OF equals to OD, they are both the radii of the circle, therefore they are equal to each other. OF equals to OD. In addition, CF equals to CD. Here CF equals to CD according to rule number 2. And finally, OC is a common side that belongs to both triangles, so OC equals to itself. It's a common side. So we actually proved that all the three sides of the pink triangle OFC are correspondingly equal to all the three sides of the orange triangle ODC. Therefore, those two right triangles can go into each other according to side rule. Triangle FCO can go into triangle ODC. According to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So this is angle FCO in the pink triangle, and it is equal to angle OCD in the orange triangle. So if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees. 2 alpha equals to 75 degrees. So alpha equals to 75 degrees. We divide this equation by 2, and finally we get that alpha and alpha equals to 75 degrees over 2, that is 37.5 degrees. So actually, this is angle alpha, that is equal to 37.5 degrees in its side. In the next step, I will copy the orange right triangle ODC in the new page, and we will analyze this orange triangle ODC. So actually, this is the orange right triangle ODC that I copied from the original drawing. This is angle alpha that is equal to 37.5 degrees, and side OD is the radius of the circle that is equal to R. In this right triangle ODC, tangents 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. We're going to find out that tangents 37.5 degrees equals to R over DC. Here we'll multiply this equation by DC, and we get that DC times tangents 37.5 degrees equals to R. Here we'll divide this equation by tangents 37.5 degrees, and finally we get that DC equals to R over tangents 37.5 degrees. So actually found out that this line 7 DC equals to R over tan 37.5 degrees in its length. So I write it down. DC equals to R over tan 37.5 degrees. From the drawing, it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. So I write it down. BC equals to BD plus DC. Repeat again. BC equals to BD plus DC. BC equals to 2 and it is equals to BD. BD equals to R over tan 30 degrees plus DC. DC equals to R over tan 37.5 degrees. So if we just found out that 2 equals to R over tan 30 degrees plus R over tan 37.5 degrees. So 2 equals to, here we take out R as a common factor from those two expressions. So R is taken out as a common factor. So what is left from this expression after we took from it R as a common factor? What is left is actually 1 over tan 30 degrees plus what is left from this expression after we took from it R as a common factor. What is left is actually 1 over tan 37.5 degrees. So 2 equals to R. Inside the brackets you have 1 over tan 30 degrees. This is actually 1.732 plus 1 over tan 37.5 degrees. This is actually 1.3032. So in conclusion, found out that 2 equals to R and 1.732 plus 1.3032 equals to 3.0352. So if we're going to find out that R, the radius that we are looking for, equals to, we'll divide this equation by 30352 and get that R equals to 2 over 3.0352. That is equals to 0.6589 units. So the radius R equals to 0.6589 units according to the second method also. So in conclusion, found out that in both methods the radius R of this circle equals to 0.6589 units. In the next step, I will summarize the lecture. We start with the first method, of course. this lecture we found out the radius r of this circle. In the drawing we have triangle ABC that blocks this circle, or this circle is inscribed by triangle ABC. In addition, we know that angle ABC, this angle equals to 60 degrees, this angle ACB equals to 75 degrees in size. And also we know that side BC of triangle ABC equals to 2 units in center. Again, our mission is to find out the radius r of this circle. So, in the first method, we did a construction, that is to say from point C, we draw perpendicular on side AB. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. Then, I copied the right triangle BDC in a new page and analyze this right triangle, triangle BDC. This is the right triangle BDC that I copied from the original drawing. In this right triangle BDC, cosine 60 degrees equals to dB over BC. So this cosine 60 degrees equals to dB over BC. BC is 2. So in conclusion, we found out that cosine 60 degrees equals to dB over 2. Cosine 60 degrees is 1/2, so 1/2 equals to dB over 2. We multiplied this equation by 2 and finally found out that dB equals to 1 unit in its length. Here, this line segment dB equals to 1 unit in its length. We continue to focus on the right triangle DBC. This right triangle DBC, sine of 60 degrees equals to DC over BC. So sine of 60 degrees equals to DC over BC, and BC is 2. And sine of 60 degrees is square root of 3 over 2. So in conclusion, we found out that square root of 3 over 2 equals to DC over 2. We multiplied this equation by 2 and finally found out that DC equals to the square root of 3 units in its length. Here, this line segment DC equals to the square root of 3 units in its length. We continue to focus on this right triangle DBC. On this right triangle DBC, the sum of the angles must be equal to 180 degrees. So which angles we have inside the right triangle DBC? We have this angle that is 90 degrees plus this angle that is 60 degrees. 90 degrees plus 60 degrees, it is 150 degrees. So the missing angle here must be equal to 30 degrees. It is given as the question that the big angle ACB, this angle equals to 75 degrees in its size. So the big angle minus the small angle, this angle is equal to 30 degrees in its size, must be equal to the missing angle, angle ACD. So the missing angle ACD will be equal to the big angle that is 75 degrees minus the small angle that is 30 degrees. 75 degrees minus 30 degrees, it is equal to 45 degrees. The missing angle here ACD equals to 45 degrees in size. In the next step, I copied the right triangle ACD in a new page and we analyze this right triangle, triangle ACD. This is the right triangle, triangle ACD that I copied from the original drawing. The sum of the angles in this right triangle, triangle ADC, must be equal to 180 degrees. We have already found out that this angle equals to 45 degrees. This is the right angle. So 90 degrees plus 45 degrees, it is equal to 135 degrees. So the missing angle here must be equal to 45 degrees. In order to complete the sum of the angles in this right triangle DCB to 180 degrees, the missing angle here must be equal to 45 degrees. So those two angles, they are equal to each other, and we have the rule that in front of equal angles in the triangle, there are equal sides. So in front of those two equal angles, we have those two sides that must be also equal to each other. So AD must be equal to DC, because they are located in front of those two equal angles. But we have already found out that DC equals to the square root of 3 units. So we can write here that DC equals to the square root of 3 units, and from this equation AD equals to DC equals to the square root of 3 units, we will derive that AD also equals to the square root of 3 units in its length. Here AD equals to the square root of 3 units in its length, and here also AD, line segment AD equals to the square root of 3 units in its length. We continue to focus on this right triangle, triangle ADC. On the right triangle ADC, according to the Pythagoras theorem, AC squared equals to AD squared plus DC squared. Again, AC squared equals to AD squared plus DC squared. AC squared that is the square of the product, equals to AD squared. AD is equal to 3, therefore AD squared is equal to 3 squared, that is 3, plus DC squared. DC is also square root of 3, therefore DC squared is equal to 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. We took out of this equation, and we found out that AC equals to the square root of 6 units in its length. Here, side AC of this triangle ABC equals to the square root of 6 units in its length. In the next step, I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is inscribed by a triangle ABC, the radius R equals to the area of triangle ABC over the semi-perimeter of the same triangle ABC. The semi-perimeter of any triangle is equals to the perimeter over 2. The drawing of this rule number 15, is here. This is the drawing of rule number 15. We have a circle that is inscribed by this triangle ABC. So the radius R of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. We can actually implement rule number 15, because actually we can implement rule number 15 whenever we have a circle that is described by a triangle. So according to rule number 15, the radius R of this circle will be equal to the area of triangle ABC over the semi-perimeter of the same triangle ABC. I'll repeat again. Now, original drawing, the radius R, according to rule number 15, the radius R will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle ABC. The semi-perimeter is S, of course. So the area of triangle ABC, the area of any triangle equals to the base of the triangle times the height to the base over 2. And we have to divide it by S, that is the semi-perimeter of triangle ABC. We choose the base of this triangle ABC as AB, and therefore the height to the base is CD. Again, the base is AB and the height to the base is CD, divided by 2, and we have to divide it by S, that is the semi-perimeter of the same triangle ABC. AB equals to the square root of 3 plus 1, and DC equals to the square root of 3. Again, AB equals to the square root of 3 plus 1, and DC equals to the square root of 3 divided by 2, and we have to divide it by S. The semi-perimeter S equals to the perimeter over 2. The perimeter of triangle ABC equals to sum of its side lengths. That is actually AB plus AC plus BC. And if we divide the perimeter by 2, we get the semi-perimeter S. AB is square root of 3 plus 1. AC is square root of 6. And BC equals to 2 units in its length, according to what is given as the question. And we have to divide it by 2. This expression equals to the area of triangle ABC. That is actually 2.366 square units. And this expression is the same perimeter of the same triangle ABC. The value of this expression equals to 3.591. So the radius R equals to 2.366 over 3.591. That is actually 0.6589 units. In conclusion, found out that the radius R of this circle equals to 0.6589 units. In the next step, I presented to you how to find out the radius R of this circle according to the second method. In the second method, we defined the center of this circle, this point as O. We defined the point of tendency of tangent AB with this circle as C. We defined the point of tendency of tangent AC with this circle as F. And finally, we define the point of tendency of tangent BC with this circle as D. We join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself. Therefore, OD is the radius of this circle that we defined as R. We have the radius OD that is drawn to point D, that is the point of tendency of tangent BC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule number 1. Likewise, we join points O and D together by a straight line. OE is the radius of this circle that is equal to R. According to our definition, the radius OE is drawn to point E, that is, therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Likewise, we join points O and F together by a straight line. OF is the radius of this circle that is equal to R. The radius OF is drawn to point F, that is, and therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. Then, we implemented in this drawing rule number 2. We have here the common external point C. From the common external point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. Here, CF equals to CD according to rule number 2. In the next step, we focus on the common external point B. From the common external point B, we have two tangents to this circle, tangent BE and tangent BD. And according to rule number 2, they are equal to each other. That is to say, BE equals to BD. According to the third rule number 2. Then we join points O and B together by a straight line, and we join points O and C together by a straight line. Then we prove that the green right triangle EOB is congruent to the yellow right triangle OBD. Why those two right triangles congruent to each other? First of all, OE equals to OD, they are both the radii of the circle, therefore they are equal to each other. In addition, BE equals to BD according to rule number 2. BE equals to BD according to rule number 2. And finally, BO is a common side that belongs to both triangles, so I can write down that BO equals to itself is a common side that belongs to both triangles. So actually prove that all the three sides of the green right triangle BEO are correspondingly equal to all the three sides of the right yellow triangle BOD. Therefore, we proved that those two right triangles can go into each other according to side rule. But from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if this angle is theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees. Here, 2 theta equals to 60 degrees. We divided this equation by 2 and finally found out that angle theta equals to 60 degrees over 2, that is 30 degrees. So this is angle theta, that is equal to 30 degrees in its size. Then I copied the right yellow triangle BOD in a new page and we realize this right yellow triangle BOD. This is the right yellow triangle BOD that I copied from the original drawing. Here triangle 30 degrees equals to OD over BD. OD is R, so triangle 30 degrees equals to R over BD. Triangle 30 degrees equals to R over BD. We multiplied this equation by BD and finally found out that BD times triangle 30 degrees equals to R. Here we divided this equation by triangle 30 degrees and finally found out that BD equals to R over triangle 30 degrees. So here BD, this times BD equals to R over triangle 30 degrees. We repeated on the same process on those two right triangles. We proved that those two right triangles can go into each other according to side rule. I repeat on this proof quickly. OF equals to OD, they are both the radii of the circle, therefore they are equal to each other. CF equals to CD according to rule number 2. Here, CF equals to CD according to rule number 2. And finally, CO is a common side that belongs to both triangles, so CO equals to itself is a common side that belongs to both triangles. In conclusion, we found out that those two right triangles can go into each other according to side rule. All the three sides of the right triangle OFC are correspondingly equal to all the three sides of the right triangle OCD. Therefore, those two right triangles can go into each other according to side rule. From the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other. So if one of those two angles is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees. Here, 2 alpha equals to 75 degrees. We divided this equation by 2 and finally found out that angle alpha equals to 75 degrees over 2, it is 37.5 degrees. So this is angle alpha, that is equal to 37.5 degrees. Then I copied the right orange triangle ODC in the new page and realized this right orange triangle ODC. This is the right orange triangle ODC that I copied from the original drawing. In this right triangle ODC, times 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. Times 37.5 degrees equals to R over DC. We multiplied this equation by DC and finally found out that DC times 37.5 degrees equals to R. Here we divided this equation by times 37.5 degrees and finally found out that DC equals to R over times 37.5 degrees. So here this line segment DC equals to R over times 27.5 degrees in its length. From the drawings it's very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. Okay, again, BC equals to BD plus DC. BC is 2 and it is equals to BD. BD is R over times 30 degrees plus DC. DC is R over times 37.5 degrees. So in conclusion, found out that 2 equals to R over times 30 degrees plus R over times 27.5 degrees. So 2 equals to, here we took out R as a common factor from those two expressions. So inside the brackets, from this expression we left only with 1 over times 30 degrees, and from this expression, after we took from it R as a common factor, we left only with 1 over times 27.5 degrees. So in conclusion, found out that 2 equals to R. Inside the brackets we have 1 over times 30 degrees plus 1 over times 37.5 degrees. So 2 equals to R, and 1 over times 30 degrees equals to 1.732 plus 1 over times 37.5 degrees, that is equals to 1.3032. In conclusion, found out that 2 equals to R. Inside the brackets we have 1.732 plus 1.302, that is actually equals to 3.0352. So in conclusion, found out that 2 equals to R times 3.0352. Here we divided this equation by 3.0352 and finally found out that R, the radius that we are looking for, equals to 2 over 30352. That is actually 0.6589. So the radius R of the circle equals to 0.6589 units. So actually in both methods we found out that the radius R of this circle equals to 0.6589 units. Okay, thank you very much.